In this presentation, I'm going to show the results of the project at urban application of the ELS at urban wastewater treatment plants in Gandia and Wulpen. First, an overview of the companies operating these wastewater treatment plants. Aquafin is fully owned by the Flemish region, operating key wastewater infrastructures in Flanders. Aquafin operates 332 wastewater treatment plants, more than 2,000 pumping stations, with more than 7,000 kilometers of pipes. Their treatment results show more than 99% of compliance with all the standards of their wastewater treatment plants, with a financial turnover for the Flemish region of almost 600 millions of euros. Global Omnium, operating Gandia Wastewater Treatment Plant, is a business group of the integral water cycle with headquarters in Valencia, Spain, and in the last 5 years we have executed more than 30 projects with more than 5.5 millions of euros executed. It has more than 135 years of experience, international presence in Latin America, USA, Africa, and Middle East, and it operates drinking water treatment plants and also wastewater treatment plants. So we have brine generation and coagulant consumption in the same company as operating in integral water cycle with more than 2,500 workers in the group. Gandia Wastewater Treatment Plant is located in Spain near the Serpis River. It doesn't have a phosphorus limit in discharge with discharging to the sea, and it treats around 40,000 cubic meters per day of wastewater. Wulpen in Belgium has a 2 milligrams phosphorus per liter limit discharge, treating around 16,500 cubic meters per day of wastewater. The results of the coagulant production. Firstly, we used iron electrodes, but we experienced a faster deterioration than expected due to the type of brines treated in the process. We experienced electron delamination and breakage, which increased the current tension and the energy consumption in the system, implying also an increase in personal maintenance hours, as you can see in this picture, where the deterioration of the electrodes is shown. On the other hand, when using aluminum electrodes, there was a lower delamination and breakage, so a higher lifetime than when using iron electrodes. So the aluminum electrodes were the ones selected to produce the alternative coagulants, hence producing aluminum-based coagulants substitutes of PAC. In this image, we can see the process. New anodes were introduced in the system. The electrolytic cycles were carried out. Once they were spent, the removal of the anodes and cathodes for the reactor was done. Cleaning of the cathode had to also be done. And then the installation of the new anodes and the clean cathodes in the system to continue producing more coagulants. About the coagulant production, in this graph, we can see the metal concentration, the aluminum concentration, versus the electrolysis time for the two current densities applied. What we can see is that, as expected, the higher density produced a higher metal concentrations in the coagulants. During the production of the coagulant at the higher current density and at 2 times the minimum contact time applied, it was obtained a metal concentration in the coagulants of 977 milligrams of aluminum per liter in using the brines of Gandia, and 910 average concentration using the brines of nearby Wulpen. In this graph, we can see the energy consumption versus the electrolysis time for the same current densities applied. What we see is that the lower current density applied show a lower energy consumption, but the higher one was used to maximize the metal concentration in the brines. During production, as we can see in this table, Gandia wastewater treatment plant had brines with higher conductivity, so an energy consumption of almost 15 kilowatts per hour per kilogram of aluminum was obtained, while in Wulpen this energy consumption was higher due to the lower conductivity of the brines produced in Wulpen. To guarantee a safe application of the waste-to-coagulants in urban wastewater treatment plant, respirometry tests were carried out to evaluate toxicity both on autotrophic and heterotrophic bacteria. This was done using different samples of activated sludge and adding as a concentration of the waste-to-coagulant using different type of brines. And what we can see in this table is how the ammonium uptake rate was higher when using the waste-to-coagulants with the two type of brines tested, and also the heterotrophic respiration was higher when using this the waste-to-coagulant, which means that coagulant didn't inhibit the biological process, and this guarantees a safe application in the system. Also, yard tests were carried out at different aluminum concentrations, targeting phosphate removal, with selecting doses from 5 to 20 milligrams of aluminum to be scaled up during the application in the pilot. The operating conditions during the validation treating urban wastewater in Gandia was to produce the coagulants as mentioned before, with the objective to reach the maximum aluminum concentration and in order to have a higher valoration of each volume of brines. The applied current in the electrolytic system was fixed with a higher current density using aluminum electrodes and the higher contact time to maximize aluminum concentration. The electrolyte was a mixture of two brines with conductivity ranging from 30 to 40 millisieverts per centimeter and pH ranging from 5 to 7. You can see in these pictures the prototype installed in Wulpen and in Gandia. The coagulant application was done in Gandia, treating effluent from the first clarifiers of Gandia wastewater treatment plant. The treatment capacity was set at 1 cubic meter per hour, and the coagulant was applied in the biological reactor of the pilot unit that we can see in this picture with a static clarifier. In this table, we show the results at different doses from 0, 5, 10, and 20 milligrams of aluminum per liter, targeting CO2, COD, phosphate, also showing the removal of total phosphorus, suspended solids, and also the turbidity. What we can see in this table is how the optimum dose was fixed at 10 milligrams of aluminum per liter, obtaining around 60% removal of total phosphorus and 76% of COD. with average turbidity removal of 85%. Hence, as a conclusion of this validation in urban wastewater, the brines and metal wastes were correctly valorized to produce the waste-to-coag coagulants. The electrolysis concept was correctly scaled up from previous projects, and the waste-to-coag coagulant was technically feasible to treat urban wastewater in Gandia. Thank you for your attention, and you can follow us in our social channels.
LIFE Waste2Coag has received funding from the LIFE program of the European Union.